Hi, on the previous lecture, we saw the working principles and typical configurations of UASB reactors, and in this lecture, I'm going to talk about design and operation of UASB reactor for sewage treatment, the part 2. So, what are the current design criteria of UASB reactors? Again, remember recalling for this point that we saw in the previous lecture, all details are well covered in this book, in this open access book, Anaerobic Reactors for Sewage Treatment, Design, Construction, and Operation, specifically in Chapter 4, but also some aspects in Chapters 5 and 6. In this slide, we have a schematic configuration of a UASB-based sewage treatment plant, where you can see that not the UASB reactor is the component of the plant. We always need a preliminary treatment unit that's very important for the good functioning of the anaerobic reactor. So in here, I'm going to talk a little bit about screens, about sieves, about grit removal, and this is a very important part of the treatment plant to protect and to guarantee the good functioning of the UASB reactor. And in here, we're going to see in details all these internal components of the reactor, but also here we call attention for the biogas production that we collect on top of the three-phase separators. And for the biogas, we need a special gas collection system, a gas flare to destroy the methane to avoid greenhouse gas emissions. We have also sludge production, and we need to take care of the sludge in a good manner. This sludge, although it's withdrawn in a, I would say, high concentration, around 4 or 5% of solids content, but still the solids concentration is high, we still have a big amount of water. So we need a sludge dewatering unit to reduce sludge volume, to a proper management of the sludge outside the plant. The sludge, after we dewater, we should give a destination. Usually, landfills is a common destination in developing countries, but it's not a proper destination form. So we can discuss this about what can be done with the sludge after it's dewatered. And also, as the efficiency of the UASB reactors, of the anaerobic reactor, usually stays around 70%. If we need a higher efficiency than that, so we need a post-treatment unit. And Thiago will have a specific lecture on post-treatment options to see what can be used to complement the UASB reactor treatment to have an overall efficiency of the plant above 85-90%. So this topic of post-treatment will be covered in the next lecture. And also, I'd like to call attention that some factors are site-specific and they determine the exact configurations and dimensions of the functional units. I'll be covering in the next slides most of the details of the components of the UASB reactor, but before that, I'd like to call attention for some aspects just before the wastewater goes inside the reactor. The first one is sludge temperature. So sludge temperature is a crucial aspect because it affects hydrolysis. As we know, the hydrolysis phase, Julius has covered this in a previous lecture. So the hydrolysis is very ineffective if the temperature is below 15, 18 degrees. So as it is almost impossible to heat the reactor when treating domestic sewage because the flow rates are usually very high because the concentration of COD and BOD are proportionally low in comparison with industrial effluents. So it's almost impossible to heat up the reactor when treating this liquid phase. So the temperature of the wastewater should be above 15, 18 degrees for the UASB reactors to become feasible for wastewater treatment. This is because the development of the anaerobic treatment for sewage treatment is more applied in warm climate in tropical countries like Brazil, like India, like some African countries, Middle East, for instance. So the temperature in these countries, the temperature of the wastewater, not the ambient temperature, the temperature of the wastewater is usually above 20 degrees Celsius. So this is why the applicability of anaerobic treatment for sewage, for domestic sewage, is more developed, is more applied in these warm climate countries. Another point is about guidelines for the design and also in some cases for operation of UASB reactors. This is well established in some countries, for instance in India and also in Brazil. Since 2011, we have the Brazilian standards for the design of UASB reactors for sewage treatment. So those two are very important aspects when we want to have good designs of this sort of reactors. And as I said in the previous slide, a well-designed pre-treatment unit is of extreme importance for the overall performance of the sewage treatment plant. If you don't have a good design of the preliminary treatment, the functioning of the UASB reactor will not be good. So it's very important to pay attention in this topic of having a robust design of the preliminary treatment units. In this topic, we call attention here for screens and sieves. So I'm not going to detail this, but we can see this later in the slides and also in the book. So for small-scale treatment units, there are some recommendations in terms of medium screens, followed by fine screens or ultra-fine screens. And here are some indications of the mesh of these screens. And for medium-sized and for large-scale treatment plants, there are also some recommendations that are in the Brazilian guidelines in terms of coarse screens that should be followed by fine screens, and also is compulsory now since 2011 to have sieves, apertures varying between 0.5 and 6 millimeters. Usually the more common apertures are between 3 and 4 millimeters. So with the use of these screens and sieves, we avoid the entrance of solids in the reactor, and the entrance of the solids are very detrimental for the function of the reactor, because it can provoke obstruction of the pipes, for instance, in the distribution chambers, as we're going to see later. So it's very important to get rid of the solids before the wastewater goes inside the anaerobic unit. And if it goes inside, it can also provoke problems regarding the quality of the sludge, because these solids will take part of the sludge that will be withdrawn from time to time. And this will also be a part of the scum that's formed, as I called attention also in the previous lecture. The scum formation inside the three-phase separator, it can be full of solids if we do not avoid the entrance of these solids in the plant. And a final recommendation for the preliminary treatment is regarding the grid chamber. So the avoidance of sand to enter the reactor is very important. Otherwise, the sand, the solids, these mineral components that are present in the wastewater will deposit in the lower part, in the digestion compartment of the reactor, and this will create dead zones. This will avoid mixing. So it's very important to have a robust design of the grid chambers. So this is the recommendation in terms of surface loading rate, 1,000 cubic meters per square meter per day. So this is the maximum surface loading rate verified by the maximum flow rate that goes inside the reactor. So those are important aspects just before we go to the design criteria, parameters, and guidelines of the UASB reactors. In this slide, we have a picture, one example of one step screen sieve, the aperture around 5-6 millimeter, used in one big sewage treatment plant in our city, in Belo Horizonte. And here we can notice the amount of solids that is retained in the sieve, as plastic, as ear tips, and other solids that are usually present in the wastewater. Or if the sieve was not present, all these solids would go inside the reactor and would cause problems in the distribution pipes, either accumulating the sludge or in the scum, and sometimes even blocking the outlet of the reactors. So this is a exemplification of one type of sieve that can be used. There are several types available by the manufacturers. Now we go more specifically to the current design criteria for the UASB reactors themselves. We call attention here that the design is mainly governed by the hydraulic retention times. It means the hydraulic loading rate, by the upflow velocities, by the characteristics of the sewage, and there are some other construction and operational aspects. I call attention here for the hydraulic loading rate, or the opposite, the hydraulic retention times. As the domestic sewage is usually characterized as a low concentration effluent, BOD around the 250, 300 milligrams per liter, COD around 500, 600 milligrams per liter. We know that in some countries, like for Jordan, Julius has called attention about this in many lectures, in many previous lectures. In some countries of Middle East, for instance, the wastewater tends to have a higher concentration. For instance, COD around 1,000 milligrams per liter, sometimes even higher. But in most of the countries, at least in Latin America, most countries present a low concentration wastewater with COD around 500, 600 milligrams per liter. So it means that the design of the reactor is not governed by the organic loading rate, but by the hydraulic loading rate. So the size, the volume of the reactor will be dictated by the flow rate, and that's because the hydraulic retention time is the most design parameter of importance, because the volume will be dictated by the hydraulic retention time and not by the organic loading rate. Different from what happens when we are dealing with industrial effluents. The upflow velocity is a parameter of it's very important for the design, because if the upflow velocity is above, for instance, 0.7 meters per hour, we're going to have a tendency of washing out solids from the digestion compartment to the settler compartment. And during peak flows, we have the risk of losing too much solids. And if the upflow velocity is very low, you can also have problems of mixing. So these two design parameters are very important, and I'm going to talk about them more deeper in the next slides. Okay, now I'm going to focus on the design criteria for the UASB reactors, specifically for the UASB reactors. So before we go to every design criteria in specific, we call attention that first, the design is mainly governed by the hydraulic retention times, in other words, by the hydraulic loading rates and not by the volumetric organic loading rates. For instance, kilograms COD per cubic meters of a reactor per day. So this is not important because we are talking about a wastewater that has a low concentration of organic matter. So what really matters for us here is the hydraulic loading rate. In other words, the hydraulic retention times is the main design parameter for sizing the reactor, for determining the volume of the reactor. Also, the outflow velocities, I'm going to talk more about this in the next slides, but also by the characteristics of the sewage. For instance, sulfate content. It's important to say that in most wastewater treatment plants, at least in Brazil and Latin America, it's not very common to monitor sulfate concentration in the incoming wastewater. But for anaerobic process, this is very important because the sulfate will be reduced to hydrogen sulfide inside the reactor, and then we are going to have the production of H2S. And with H2S, we can have odor problems, we can have corrosion problems, but we can also have inhibition problems if the sulfate concentration is too high. And also, if you produce H2S in the effluent, because the sulfate will be reduced to H2S, if we have one aerobic post-treatment unit, this sulfite concentration will demand oxygen for its oxidation. So it's very important to monitor sulfate content in the incoming wastewater before you decide for the design of an anaerobic treatment plant. So this is very important because if the sulfate concentration is very, very high, sometimes the anaerobic process may not be the most indicated one. For giving one range of concentrations for the wastewater in your conditions in Brazil, usually the sulfate concentration varies from 40 to 60 milligrams per liter. In some cases, goes up to 100 milligrams per liter. But I would say that it's not common to have a wastewater with more than 100 milligrams per liter of sulfate. In your case, if you have a very high concentration of sulfate, for instance, because you have a contribution of industrial effluents, for instance, from tanneries, pay attention, because if you have high sulfate concentrations, you are going to have high sulfide concentrations in the effluent, high H2S concentrations in the biogas, a lot of much more problems with corrosion, so pay attention in this point. And besides these 3 points, also by various construction and operational aspects that I'm going to call attention for these points later. So here, the design criteria regarding hydraulic retention time. In other words, to the hydraulic loading rate. So as the design, the process is governed by the retention time of, or in other words, by the flow rate of the wastewater, the hydraulic retention time is dependent on the temperature of the wastewater. And here we have 3 ranges. If the wastewater between 16 and 19 degrees, so usually we demand higher hydraulic retention times, here for the daily average flow, and here for the minimum that should be kept from during 4 to 6 hours inside the reactor. As the temperature go up, for instance, between 20 to 26 degrees, the hydraulic retention times for the average flow rate, usually above 6 up to 9 hours. And if the temperature is even higher, above 26 degrees, we should have even lower hydraulic retention times, but we do not recommend retention times lower than 6 hours, exactly because the volume of the reactor become too small that it has less operational flexibility, especially in terms of sludge storage in the reactor. So we do not recommend sizing the reactor with retention times lower than 6 hours, even if you have temperatures above 26 degrees. And you can see here that these recommendations are not new. We have been using this recommendation since a work by Lettinger and Paul in 1991, and we still keep using this reference, but sometimes adjusting the range that we have been using for different temperatures. Another point of importance is the sludge load. It means the amount of organic load that we apply per kilogram of volatile solids of biomass of sludge inside the reactor per day. So the sludge load is the product of the flow rate times the COD concentration, and here we have the COD load, divided by the sludge mass that we have inside the reactor. We have means to determine this sludge mass by taking samples of sludge at the different heights of the reactor, as we're going to see in the final topics of this lecture. And this sludge load has a direct relationship with the specific methanogenic activity of the sludge, as Julius called attention in his lecture, in a previous lecture. So it means that we should keep amount of sludge inside the reactor sufficient to treat the organic load that is going inside the reactor. Upflow velocity is another very important parameter, because as the process is very much dependent on the hydraulic conditions, so it means that the upflow velocity is also of very importance. When treating domestic sewage, usually we do not have granulation. It means that we do not have granular sludge that has a very good settling property. When we are treating domestic sewage, we have more affluent sludge, and the settling velocity, the settling capacity is not as good as the granular sludge. So we should keep the velocity between a certain range to avoid dead zones. If the upflow velocity is very low, we can have a bad mixing, and sometimes the accumulation of solids inside the reactor that cannot be moved. And on the other range, on the opposite, if we have very high upflow velocities, we might not keep the sludge inside the reactor. It means we favor the washout of solids to the settler compartment, and also with the final effluent, if you not can retain these solids in the settler compartment. So here we have the values that are recommended for the average flow velocity between 0.5 and 0.7 meters per hour, and also recommendation for maximum flow and for temporary peak flows. The maximum flow is because the flow rate varies along the day, along the hours of the day. We have peak flows most of the time in the later hours of the morning, 10 a.m., 11 a.m., sometimes midday, because we have more water consumption at the early hours of the morning, and this water consumption will be transformed to wastewater that takes some time to enter, to arrive at the sewage treatment plant. So it's important to verify these upflow velocities for the average flows, for the maximum flow, but also for the temporary peak flows. For instance, if you have some contribution of rainwater for a few minutes or a few hours during the day, respecting these maximum 2 to 4 hours peak flows, it's important, even during these peak flows, the upflow velocity do not surpass, do not overcome 1.5 meter per hour. Now we go to some important components of the UASB reactor that are also very important for the good functioning of the system. I would say that the influent distribution systems is one of the most important systems for the design, for a good design of the UASB reactor. It's very important because as the wastewater has a low concentration in terms of COD, it means that the biogas production will be low, proportionally low, comparing, for instance, with a very high concentrated industrial effluent. So if the COD concentration is low, if the biogas production is low, the mixing that is promoted by the upward movement of the biogas bubble, as we mentioned in a previous lecture, will be poor. So we do not have a good mixing due to the biogas production because the biogas production is low. So we are dependent very much on the upflow movement of the liquid itself, of the incoming wastewater. So that's because the influent distribution system is very important, because the mixing, to avoid dead zones, to have a good contact between biomass and the organic matter, to have the whole or the full volume of the reactor operating, we depend on a very good distribution systems. And how we do this? We need to have distribution chambers or distribution compartments. We need a certain number of inlet distribution pipes. And we have to define the number of distribution pipes to allow a good distribution inside the reactor. I'm going to talk about these 3 points in the next slides. Here we have some examples of distribution chambers located on top of the reactors. Here we have one distribution chamber, a very simple one, I would say more used in the first generation of circular UASB reactors. And here we have the incoming wastewater and chambers in the outer part, and on the bottom of each chamber there is one pipe that goes to the lower part of the reactor. And here we have another model of distribution chamber. For bigger reactors, we have 1, 2, 3, 4, 5, 6 maybe distribution chambers, each one dividing the wastewater in a certain number of pipes, and these pipes distributes the wastewater at the lower part of the reactor, and from that point the reactor has the upflow movement, as we are going to see. Here is another example of distribution chamber. If you compare this distribution chamber with this one here, in here we have a lot of pipes on the top part of the reactor. So maybe for the reactor to walk along this slab is not so easy. There is a risk of accident. So in this case, we have a much cleaner upper part of the reactor, so it's much easier for the operator to do the operation activities that are necessary, especially to unblock these distribution chambers that tend to block, especially if the preliminary treatment unit is not a good one. For instance, if there is no sieve, there are no sieves in the preliminary treatment unit, we are going to have solids in the distribution chambers that can block the pipe that goes to the bottom of the reactor, because this pipe has a diameter usually limited to 75 millimeters, 3 inches. So it's a good example of a distribution chamber on top of the reactors. In this specific case, we have 6 distribution chambers, 1, 2, 3, times 2, 6, and each chamber has 32 pipes leaving from this small distribution chambers here. So it means that we have 6 distribution chambers multiplied by 32 pipes. We have 192, if I'm not wrong, distribution pipes inside the reactor. So it's a lot of pipes, but this is very important because each pipe has a specific location inside the reactor to distribute the wastewater at that point, and from that point onwards, we have the upflow movement using the whole amount of sludge, of biomass, along the whole area of the reactor, of the bottom area of the reactor. Here we have examples of distribution pipes. In here, vertical pipes. So these sort of pipes, the vertical ones, are related to this distribution chamber. You see here the distribution pipes. They are distributed on the top in different points, and they go on the vertical position until the bottom of the reactor, as we can see here. And there is one support to keep this pipe in position. Is important to pay attention on the design of these supports to avoid this pipe moving or sometimes losing from this support, and then we are not going to have the guarantee that the wastewater is being distributed at the right position at the bottom of the reactor. And here we have another example. There is a curve, a bend of the pipe is a pipe that allows this bending, but there is also support to keep the pipe in the right position. You see that you have many pipes as necessary, as we are going to see in the next slide, to determine the amount of pipes that are necessary. And here, some possibilities of distribution pipes. Usually they are assembled, installed 10 to 15 centimeters above the lower part of the reactor, exactly to distribute the wastewater, the organic matter, to have the good contact with the sludge that is around here. And in some cases, we have to adapt the distribution pipes. We cannot have a free space available. For instance, if it's an existing reactor that we need to implement new pipes, it's not possible to have support types like this one here. We can think in fixing the pipe with different, for instance, with a bricks or concrete, and open one window in its lateral, but also keeping the height above the bottom around 10 to 15 centimeters. Okay, how many distribution pipes we need to cover the whole area, the bottom area of the reactor, to have a good distribution, a good mixing, to take most of the volume of the reactor, to take most of the mass of sludge that we have inside the reactor. So we have this table that helps us to determine the number of distribution pipes. It depends on the sludge type, if it's flocculent or granular. It depends on the organic load rate applied to the reactor. And with this, we determine the influence area of each distribution pipe. In the case of domestic sewage, usually we have this sort of sludge, dense and flocculent, concentration just above 40 kilograms total suspended solids per cubic meter. It means 4% sludge. The granular sludge is more common, is usual to happen, to develop for industrial effluents. So I'm not going to talk about granular sludge here because it's more applied. These guidelines here are more indicated for treating industrial, high concentrated industrial effluents. But why the flocculent sludge differs from one reactor to the other, and why it's important to determine the amount of distribution pipes? Because the lower the concentration is, easier is to mix this sludge because it's not very much concentrated. So in summary, the granular sludge is more difficult to mix, to move, and because of that, most of the times we need more distribution pipes that cover a smaller influence area. The smaller the influence area, more pipes we need. That's the message. And when I go to floc-length sludge, it's easier to mix, easier to move, and usually we would need less distribution pipes. But if the organic load is also low, the biogas production will be low, and we are not going to have good mixing due to the organic loading rate. It means due to the biogas production. So we also need a lot of distribution pipes because the influence area will be smaller. Let's compare, for instance, in this case here, this dense and floc-length sludge with a low organic loading rate applied, 1 to 2. And then if you go here with a sludge that is even of lower concentration, but if you have a higher organic loading rate, above 3 against 1 to 2. And you see here that the influence area can be much higher, 2 to 5 square meters per pipe. It means that we have, let's say, one reactor with 100 square meters of bottom area. If you apply 2 square meters per distribution pipe, it means that if we divide 100 by 5, we would need 20 distribution pipes. That's the way we calculate, we estimate the number of distribution pipes. And here, for the same area, if you could have, let's say, 2 square meters per distribution pipes, for the same area, 100 square meters divided by 2, we, in this case, we would need 50 distribution pipes. It means 50 distribution pipes here against 20 distribution pipes here. So it makes a big difference in the number of distribution pipes, and this is important to determine according to each specific design itself, dependent more specifically on the sludge loading rate, because the type of sludge usually will be this one here, dense and floc-length with concentration usually above 4%. So the final message is that for domestic sewage treatment, usually we estimate the number of distribution pipes considering 2 to 3 square meters per distribution pipe. Now, another very important component, device of the reactor, UASB reactor, is the three-phase separator, as we called attention in the previous lecture. And here we show one section of one reactor with two three-phase separators, one besides the other. And here we have to comply with various design parameters or guidelines. For instance, we have to determine the correct angle, and this angle here usually should be above 50 degrees to allow the return of the solids to the settler, to the digestion compartment. We have to define the aperture that we have here from the digestion to the settler compartment. So this aperture should not be too small, otherwise the upflow velocity through these apertures will be very high and will tend to carry solids to the digestion compartment and can, in this way, overload the digestion compartment. So we should define this aperture here. This is the double of the aperture between three-phase separators. We have to determine the height of this cone section of the three-phase separator, of this tilted, inclined part of the three-phase separator, also the height of this rectangular part of the three-phase separator. So H2, H1 defines the depth or the height of the three-phase separator. These apertures here, if you subtract or deduct the width of the reactor, we are going to have the size of the lower part of the three-phase separator. So there are many aspects that we should comply here, like the hydraulic retention time inside the settler compartment, the surface loading rate in the settler compartment, the velocity through the apertures, the biogas release rate in this interface between liquid and biogas, the slope of the three-phase separator. So there are many aspects that we should comply here. And the indication that we give, the suggestion that we give, usually we comply, usually we reach a good design when we use this magic number of 3 meters between the axis of two three-phase separators. For instance, in here, representing two three-phase separators, we would have the width of the reactor of 6 meters, 3 meters from the wall to the middle, and another 3 meters through here. And if we subtract the aperture here and the apertures here and here, we're going to have the width of the three-phase separator. And we need to define the width of the gas chamber. So there are many aspects here. So I recommend you to go to the book to see this in more details, but also to use the free software that we made available that goes together with these lectures, okay? So there is a software that we made available that considers the use of one modular three-phase separator that already has these proper dimensions that we can accommodate all the parameters. We can comply with all parameters that are necessary for the good functioning of the three-phase separators. And here, I mentioned in the previous slide, the surface loading rate and the hydraulic loading rate in the settler compartments. Going back, and here, retention time in this volume here, the whole volume of the settler compartment. And the upper surface here, we determine the area, it means the width times the length of the the settler compartment. And here we can determine the volume to determine the hydraulic retention time and the area of the settler compartment to see if these parameters here are complied. So here are the recommendations for the previous parameters, for the average flow, for the maximum flow, for the temporary peak flows. And here, the recommendation for the surface loading rate in meters per hour, 0.6 to 0.8, that's slightly above the flow velocity that we mentioned before. It was 0.5 to 0.7 for the upflow velocity. Here, for the surface loading rate, 0.6 to 0.8 for the average flow. And the hydraulic retention time, 1.5 to 2 hours, again for the average flow for that volume. For the maximum flow and for the peak flows, is the same principle. It should be analyzed in the same way. Is there any problem if you have a hydraulic retention time above 2 hours? Usually not. If you have higher hydraulic retention times or lower surface loading rates, it's even better because we can retain even more solids inside the settler compartment. And in this slide, we see the guidelines for the velocities through the apertures of the settler compartment. Going back again to the picture, we're talking about the velocity here, the velocity through the apertures here. So we should determine the width, the length. It means the area of these apertures, areas in this position between three-phase separators. So the whole area, if you divide the flow by the area, we have the upflow velocity through the apertures. And here we see that they are, for the average flow, lower than maximum 2.3 meters per hour. Again, comparing with the upflow velocity in the digestion compartment, that was 0.5 to 0.7, and we see here that the upflow velocity, or the velocity through the apertures are around 4 times more than the upflow velocity in the digestion compartment. So we admit a much higher velocity here through the apertures, and also for the maximum flow, for the temporary peak flows. But if the velocity is above 2.3 for the average flow, we should increase the width of that aperture to reduce the velocity. So those are the guidelines, the indications. Here, the current design criteria for the gas system. This can vary a lot, dependent inclusive from the size of the treatment plant. But usually what we have is that we have the three-phase separator, and usually we have a hydraulic seal that allows us to put some pressure inside the three-phase separator. This height that's indicated here, that's the distance between the operational level of the settler compartment and the level inside the three-phase separator. That's the interface between liquid and gas. There is one pressure indicated by this letter H. So this letter H is indicated here. That's the distance between the level inside the hydraulic seal and the opening of this biogas pipe. And if we put water here, we put some pressure for this gas to be released, and this pressure is maintained inside the three-phase separator. This pressure is important to make it easier for the biogas to be released from this upper surface of the liquid, where usually there are one amount of scum that's formed here, but this scum should be removed from time to time. From time to time, I mean sometimes a week. It's not like a sludge. A sludge you can remove every week, every 2 weeks, but the scum should be removed maybe 2-3 times a week. I'm going to talk about this in a later lecture. So from the three-phase separator, we have a collection piping that goes to a hydraulic seal. We recommend here a gas meter, a flame trap, and minimally a flare should be used to destroy the methane if this methane is not used to recover energy. There are very important aspects here that are well described in chapter 4 of the book, but I would like to call attention here for some aspects. For instance, drain. So humidity of the biogas, the humidity can condensate and accumulate in the lower part of the pipes. So the pipe should always have one slope, and at the lower part of the pipe use to design drains to remove this condensate. Otherwise, this will block the flow of the biogas. Sometimes the flare does not work because the biogas does not arrive there, and if there is condensate here, these are going to put pressure upwards the biogas line. Another point to call attention here, the type of or the material that can be used for these gas pipelines. The recommendations are stainless steel, 316, yes, 316, 304 is not appropriate, or either high density polyethylene. Yes, this. For instance, there are some plants that use PVC. PVC, although is used sometimes, is not recommended because this material has some porosity, so is not considered in the guidelines in many countries. What else here? Oh, about biogas meter. There are many good biogas meters in the market, but we say that biogas meters based on turbines are not appropriate because this biogas is not completely clean. It can have particles, and these particles can interrupt the functioning of this turbine. So there are different gas meters that do not use moving parts inside the meter itself. This is important to use to measure the amount of biogas that's used, but I have to say that most plants that I know, they are not biogas meters because they are usually expensive. Usually they are imported from developed countries. So this is still one point for development, for having lower price gas meters to be used in this sort of reactors. Here some pictures. I'll come back to this. Sorry, so this slide here. And in here, I have shown one very simple gas system where we do not have some complicated devices. For instance, the control of pressure and vacuum is reached by this hydraulic seal that's very cheap, something like this here in the picture, no? But in some plants, they have more sophisticated gas systems that use valves for release of pressure and also to avoid vacuum. So this is in here one gas meter in this plant, and here all the biogas is being burned in this biogas flare in this plant. Although it produces a lot of biogas, biogas is not being used still for energy recovery. It's being evaluated exactly nowadays, but it has been burning for a few years. This is a waste of energy, and this should be avoided. Coming to the end of this class, I think about 3 more slides, I feel. We bring here some details of what should be predicted for sludge sampling. As I said before, we should know the amount of sludge that we have inside the reactor to see if it's in the correct range between a minimal amount capable of treating the organic loading rate that's arriving. So we should keep a minimum amount, but we should avoid one amount that goes beyond the storage capacity of the reactor. So it's important to monitor the amount of sludge, and for this we use sampling pipes installed from the bottom up to the upper part of the digestion compartment, and from these sampling points, they are shown here, simple devices, different depth inside the digestion compartment, and opening this valve, we can sample the sludge at different levels, and with this sample, we determine the concentration, and concentration times the volume that each sampling point represents, we have mass. Concentration times volume, we have the mass of sludge. If we sum up the mass of, in this compartment, of P1 with the mass of P2, P3, P4, and P4, we have the whole amount of biomass inside the digestion compartment. And with this, we can check if the sludge load that one of the first parameters that I mentioned in this lecture, we can check if the sludge load is okay, and also if we can compare if the concentration determined in this upper sampling point, for instance P5, is above, that's another magic number for you, 0.5%. Usually we want to keep the concentration of sludge in this upper sampling point maximum or below 0.5%. If you have a high concentrated sludge determined here, it means that the sludge can be already inside the settler compartment, and we somehow lose the capacity of estimating the mass of sludge inside the reactor, and also the sludge that is accumulated here, when we have peak flows, we are going to lose this sludge with the effluent. So we're going to lose efficiency in terms of particles, in terms of suspended solids. So the indication, the importance of this device, and also what we can learn from this, is to determine the mass, to see if you keep the minimum mass, usually is more than sufficient, but also if the amount of, if the concentration of sludge in the upper part here, sampled in this point here, just close to the gas deflector, is below 0.5%. So that's the guideline, that's the goal, to keep the highly concentrated sludge in the lower parts of the digestion compartment and not in the upper part. And still regarding to sludge, is the sludge discharge system. It's also very important. I call attention, I highlighted this point just at the beginning in the previous lecture, the importance of keeping the sludge between these two ranges, minimum and the maximum. And the maximum is dictated by the concentration of sludge here in the upper part. And to control the sludge between those two limits, minimum and maximum, we should discharge the sludge in a proper way, in a proper manner. And for this, all reactors should have, at least according to our guidelines in Brazil, two discharge points. One at the bottom, usually 15, 20 centimeters above the lower part of the reactor, and another sampling discharge pipe here, usually around half height of the digestion compartment. Okay? And with this pipe, we can discharge the highly concentrated sludge, and with this upper pipe, we can discharge the lower concentrated sludge. The ideal one should be discharged more sludge from this part, because it's a less concentrated, a loose sludge that's easier to lose with the effluent. But if you discharge this sludge with a lower concentration, this will result in a high volume. and this high volume can impact the dehydration unit. But even though we can preserve, we want to preserve this bottom sludge, it's good to have some discharge from this point as well, because if some inert solids, for instance sand, went into the reactor, it's good to remove part of this sludge, to remove some also part of this inert material that comes with the sludge. What is the magic number? The recommendation we give is that if we determine, the way to determine the amount of sludge, the volume of sludge that we have to determine from time to time is well also described in chapter 4 of this book. But the way we recommend is to discharge more sludge in terms of mass from this point than from this point. But if this is not possible, because this will result in very high volumes, try to discharge at least 50% from this point in terms of mass and 50% from this point in terms of mass. So this one indication that we have to have during the design, because the amount, the volume of the sludge storage tank, the size of the sludge drying beds, or the capacity of the mechanized dehydration unit, this will depend on the volume that we're going to discharge from each point. So in knowing let's say 50% from this point, I sludge here at 5% concentration. So 50% of the whole amount of mass that we have to discharge, let's say we have to discharge 1,000 kilos, 50%, 500 kilos here. 500 kilos with a sludge of 5% will give me a volume that I have to discharge from this point. And again, in the same way, 50% of mass here will be another 500 kilos. 500 kilos, but the concentration of sludge here will be possibly 2.5, 3%, and this will result in a higher volume from this point. We have to have flow meters in the sludge discharge line, and with this we can control the volume the volume we are discharging from each point. And here we have examples of discharge points, discharge pipes at the bottom and discharge pipes at the middle height of the digestion compartment. And here we have some examples of valves outside the reactor. Each discharge pipe has its own discharge valve. It's very important to discharge 1 point per time, not together. Otherwise, the less concentrated sludge will be released first. I would have a lot to say about this system and these operation possibilities, but we are going to have more time to discuss this in the next lectures, and also all the details about this are in the book. And I think this is my final slide. Okay, we have the design parameters. We discussed a little bit about important points for operation, but how are those full-scale UASB reactors performing? So we did this inventory considering 5 countries that we're not specifying the countries, of course. 5 countries, different countries. Effluent concentrations in terms of COD, BOD, total suspended solids, and here the remove efficiencies that have been reported for these full-scale UASB plants. I'm not talking about here lab scale. And here the idea of the size of the plants to see that all of them are full-scale. And here we see that most of the plants, most of the countries, the reactors are performing very well, between 60-80%. in terms of COD, BOD, total suspended solids. But also, we have one country in particular that the efficiencies are not so good. And why is that? Usually they condemn, they indicate that the operation is poor. The poor operation may be one of the reasons, maybe one of the causes, but from our experience, we cannot put all these problems in the operation. It is very probable that these reactors also has some sort of design problem or even the construction problem. So usually plants that do not perform well can be attributed to design, construction, and operation. I think this is an important message to dedicate important attention to the design, construction, otherwise the operation will not be good. And with this, I thank you very much for your attention.